So hello everyone, my name is Esther. I'm a residential low-rise building designer from Southeast Queensland. So my designs, I work primarily in climate zone 2, which is mild winters, hot summers and a nice dose of humidity thrown in. So here's just a little auxiliary dwelling or granny flat, which is currently under construction. It's just reached lock-up stage. And it's at, as Chris pointed out, we're very proud of this 9.1 star home. So let's have a look at how to achieve a highly efficient home. So why choose an energy efficient home? As building designers, we have a duty of care to the environment, and by designing efficient and durable housing, we can contribute to reducing Australia's carbon emissions. An efficient home, a highly efficient home, is also a sanctuary from heat or cold or storms and other climate extremes we may be experiencing in the future, including extended power outages. So carbon emission reductions by design, this is something that every building designer has a choice and can definitely make a difference to the future of our planet. My personal targets in the residential setting. So currently the National Construction Code, we require 6 stars as a minimum 6 out of 10 to reach the efficiency of a home. And it looks like it's going to be moving up to 7 stars in the new version of the National Construction Code, which is very exciting. So my personal design goal I do a lot of renovations. So my renovation goal is to reach 8 stars and my design goal for new builds is 9 stars. So if you're a building designer listening to this, what are your targets and what do you know about carbon in construction and how you can make a difference to the planet? That's my question for you. So what is a 9-star rating? Australia's residential energy efficiency is graded out of 1 to 10 for performance of the building. This is based on how much energy it's going to take to heat and cool the home, based on the envelope, the fabric, so what the building's constructed out of, the solar orientation, as we heard from Corey earlier on, the zoning of the building and internal zones of the building, and the glazing. A 1-star home, which is on the low end of the scale, will provide very little protection from the elements, and a 10-star home will have a year-round internal, stable, comfortable temperature without any mechanical assistance. So a 10-star home, you would expect year-round, regardless of what's going on outside, the internal temperatures will be between maybe 20 and 23, which is just about perfect. So this is what the star ratings look like on an energy consumption, from an energy consumption point of view. So this, let me just get my laser pointer. This 6-star here, this is taken, an example taken from the NatHERS website. So a 6-star house is consuming 119 megajoules of energy per square metre per year. And it's divided into heating and cooling. So this is a cool house, so it requires more energy to heat it and less energy to cool it. So this 7.1 star rating is from one of my projects. So you can see there's dramatic drop in the amount of energy required to heat and cool this building compared to this building. That's almost, well, it's a bit over half the amount of energy required to heat and cool this building. So 8.2, this is from a renovation that I've been, a very exciting renovation I've been working on lately, which is a 3-star house, which is moving to an 8-star house. So, and then 9.1, it takes a total of 23 megajoules per square metre to keep it comfortable inside, to heat and cool it. For those of you who have been reading the fine print down here, the basic, some very rough calculations, the financial cost to the resident of the building, whether it's a rental or owner occupied, it's around just under $1,000 a year cheaper to live in this house than it is to live in this house. So that's a very good example as one of the reasons we should look at highly efficient homes. So as a designer, you really need to understand how designs are assessed in order to be able to design well. So in Australia, there's two methods. There's a deemed to satisfy method, which provides you with an energy efficiency report. And this is taken directly from the National Construction Code. So you basically go through the code and you pick out your climate zone and you select the kind of construction method you're using, such as slab on ground, brick veneer, timber frame walls, concrete tile roof. And it tells you exactly how much R values those methods of construction are going to be worth, so that you can assess how much insulation you need to put in. The second version is the NatHERS assessment. So this is an actual assessment of the building on a zone by zone basis. So that's living zones, sleeping zones, washing zones of the internal of the building. It's your design will be brought into software that models the performance of the building based on the parameters entered, and a detailed report is produced. So the detailed report tells you exactly how much energy it takes to run that home in winter and summer. You don't get a similar result from the deemed to satisfy method. The deemed to satisfy method is fairly generic. As a designer who wants to give their clients a quality design, you probably should, well, you should be using the NatHERS assessment. One of the big advantages of the NatHERS assessment is that you can tweak your design. Once you've done your model, you can change parts of the design to improve or assess the impact of your changes on the efficiency of that building. So the current standard in Australia of energy efficiency stars for buildings is 1 to 10. The current standard, minimum standard that a building must achieve is 6 stars. Now, just a quick clause, that only applies to residential houses. It's different for townhouses and mass buildings. Every different building has different results. So around 17% of the NatHERS assessed houses in 2021 were below 6 stars. There are loopholes in the law. In Queensland, you can legally design a 4-star house. You can get 1 star by adding a ceiling fan to an outdoor living area, and another star can be gained by adding 1 kilowatt of solar power on your house. So a lot of rentals in southeast Queensland are designed on this model, which is not very kind for people who can't afford to buy because they pay twice the amount of power to live in their homes. So it's not a very sustainable model. So how do we avoid this as designers? How is a building energy efficient? Orientation, as we heard from Corey, brilliant presentation by the way, Corey. Insulation and glazing are the 3 main points that I address first up in my designs. So solar orientation. We want to avoid any direct sun on walls and windows during summer, and we want to minimise our east and west exposed glazing. In winter, we want to maximise direct sun on glazing, and we want to try and get, if we have any thermal mass in that building, it has to have sun on it during winter, or it doesn't work. If it can't gain heat from the sun, it's not thermal mass, it's a cool sink, which you don't want in your house in winter because we like warm toes. So here's an example, here's my example of our little 9.1 star baby who's the solar orientation. So this is midsummer. There's 0 direct sun on the northern wall or any of the windows here. We've got water tanks to the west so that any western late afternoon sun is also blocked from reaching the building. But in winter, we've got winter sun penetrating more than half of the house, which is going to make for a very beautiful internal comfortable temperature through winter. And this is a lovely drone shot, courtesy of the carpenters, showing midwinter how far that sun reaches through the windows into the house. It's really quite nice, very effective. This photo was taken around 7 a.m. So as a designer, as Corey showed, you need to use your software and become familiar with your building throughout the year and where the sun is hitting your glass, because that's really important. So this is summer, midsummer. This is at 7 a.m, 8 a.m, 9 a.m, and 10 a.m. So this window is getting a good 2.5 hours of what could be 30 degrees sun, 35 degrees. By 9 o'clock, it's very easy to be 35 degrees in our climate. So the second step, insulation. Create an airtight barrier around the skin of your building and then insulate it as much as possible. Common practice in my region is no roof insulation, so just sarking in the roof. A minimum of R2 insulation in the ceiling, so that's just above your plasterboard in the ceiling. You've got a layer of insulation sitting there. You've got R2 in the walls, and Queenslanders don't do floor insulation. We just don't do it, except maybe around Toowoomba. And it's quite common for designers to not have any specific insulation data except for maybe an R value, no section detailing and no insulation plan in their drawing sets. If you want to do efficient homes, you need to stack on the details. When a carpenter, a builder, or another tradie gets your set of plans on site, they have to interpret it themselves. If they can't see it and they can't see it really clearly, they won't build it that way. So it needs to be really clear exactly where you want the membranes and where you want the insulation to start and stop. You need to be very clear about non-standard details, things like roof lights or skylights. Make sure that the walls for the skylights that are penetrating a ceiling void are detailed. That's really important. And there should be an insulation plan, particularly on more complex renovations. There should be an insulation plan saying exactly what R value it is and where it's placed in all the different parts of the building. Here's an example of the envelope. So it should be very clear to the builder how far out you want the insulation to go, which side the membrane should be on in the roof, and any points that could be breaches in your envelope need to be addressed. So we looked at what's common in our region. This is the insulation that I put in this building. So we had R3 in the roof, that's up here. We had R6, which is very unusual to go that high. That's nearly 300 deep, that insulation. So it's substantial insulation. So R6 in the ceiling, R2.7 in the walls, which is about all you can get with mineral or rock wall. That's about the best, well, that is the best you can get in a timber frame stud wall. We don't have underfloor insulation because our winters are very mild, so the ground doesn't cool down enough to make the slab an issue. And specifics. I have brand names and I have R values and I have dimensions of insulation on all of my drawings. All my sections show where the insulation is and where the insulation and sarking is. A couple of tips. Insulating flat roofs can be very difficult, and it's very easy to make mistakes as a designer or omissions as a designer that can cause long-term waterproofing issues. So as a designer, you need to address any risks around designing flat roofs. Flat roof for me is anything under 15 degrees. Hail is a big issue in our region. It fills the gutter and then it rains straight after the hail. And so the gutter is completely filled over the top with ice. And when it rains, the rain is very heavy and it sits on top of the ice in the gutter. So essentially you've just removed all the hail, has essentially removed all of your gutters on that building and blocked them up. So the water finds it's very common for the water in a hailstorm or directly after a hailstorm to find its way into the ceiling cavity. So hail needs to be addressed in flat roofs when you're insulating. Anti-ponding, which is part of that, preventing the water to come back into the ceiling. Cathedral ceilings, you're probably going to need to seek very technical advice from experienced people. If you want to insulate a high energy efficient home with a cathedral ceiling, you'll need support. Condensation, so when you're adding all this insulation to a building, you're creating condensation problems that needs to be addressed. Ventilation goes in hand with condensation, that also needs to be addressed. And flashing details, you need a lot of flashing details. So glazing is the third key point in an energy efficient home. So glazing to wall ratios, keep the glazing to wall ratio down. Less glass, more wall. So a wall is heavily insulated. You can put R10 insulation on a wall and then put a great big pane of glass in it, and you've just removed all of the insulation. So you need to consider glass in a wall as a hole in that insulation. So glazing location, make sure it's in the right place. Try to keep it off the western wall. Try to keep it shaded at the right time of the year. The frame of your glazing is very important. What are the different thermal performances of the different materials that window frame or door frame is made out of? Energy efficient glass versus insulated glass units. So this is like low-E glass, single glazing low-E glass versus double glazing. What is the cost? What is the performance benefits? And design specifics. I can't stress this point as much. Research your products until you know the benefits, but also the potential risks and the negatives. So you need to speak to manufacturers. You need to speak to their technical specialists. You need to get to know that product. See if you can get onto a site and see it in action. Speak to the carpenters or the builders who are using the product. What do they like about it? What doesn't work? That's really important, and it makes you as a designer a much smarter designer. So detailed schedules, glazing schedules are important. We all know that. But you need to be really specific about the U values and the SHGC values. So when a builder gets a set of plans, he might often send them off to an estimator, and a builder will have his preferred suppliers. He might use a particular window and glass manufacturer that you haven't specified. So if he wants to get alternate quotes, that's fine, but he still needs to, they still need to meet the minimum requirement that you have set here. If you're specific enough here, they can send this to any supplier in Australia and they'll be able to match your energy efficiency rating without a problem. So the risks in what you can do wrong in glazing, again, poor design research. So some types of highly efficient glass are not suitable for internal or external use. They need to be protected. You should be very, very familiar with the WERS website. This is so important to designing an efficient home. And also becoming used to what the manufacturers specify. So get quotes from different suppliers and have a look at how they set out the windows so that you can specify on your drawings very, very clearly exactly what you need. So more risks, cost. An energy efficient home is going to cost more. It's going to cost more to build. You can't use the same products and get a better result. You have to pay more, get better products. So double glazing is still a novelty in climate zone 2. Subtropical climates, double glazing, most people have never used it. The Pinterest trends of glass walls and more glass walls makes it very difficult to create an efficient home if there's no insulation in it. Generic glazing that's generally used in our climate has very, very poor performance. It transmits all the heat, even if it doesn't have direct sun in summer. It's 45 degrees outside. A lot of that heat is going to be coming through the glass. Custom timber joinery, which is a much better performing frame for windows and doors, thermal wise. It can be twice the price of the same product in generic aluminium glazing. Thermally broken aluminium framing can be up to 4 times the price of generic glazing, and it might not always have the performance to match. So, expenditure versus value. Here's a quick look at our little project. It's a very small project, 50 square metres in total. We had 4 small windows, 1 medium-sized window, 2 large windows, 1 sliding door and 1 stacking door. Not a lot of glass in this building. Just enough to make it nice, but not enough, not so much. So here's some generic values of quotes that we received. Now, a quick COVID clause, these prices probably gone up by 20% in the last 4 months. So aluminium frame high performance glazing. So high performance glazing is single glazing, but it's low E, or it's tinted, or it's treated, or it's laminated. 14,000. The same windows and doors in a thermally broken frame, 26,000. So that's $12,000 more expensive. It's a big jump. Timber softwood frame with double glazing, one of the panes being high performance, 17,000. We got a price on the doors to try and get, I don't like using sliding doors in high performance buildings because they don't seal properly. So we looked at using, the client wanted sliding doors, so we had to put sliding doors in. We looked at sliding doors from a European quality hardware and seals. So this is a sliding door that nothing is going to get through. It's made from a hardwood timber frame, double glazed, high performance, similar to the softwood version. 15,000 just for the 2 doors. So that gives you an example of expenditure versus value. So how do we know if we choose the most expensive option, how do we know we're getting value for money? So we try using star ratings, the NatHERS assessment. So high performance glazing in an aluminium frame, a generic aluminium frame, we got 7 stars, 7.1 stars. Thermally broken frame, still 7 stars. It didn't give us any big benefit in this particular case. Single glazed, thermally broken frame, wasting your time. Double glazed in a softwood timber frame bumped us up 2 full stars. So this wasn't so much about the frame, it was about the double glazing. Double glazing is worth its weight in gold when you're talking efficiency in a building. So what are the risks in choosing the more affordable option? Softwood is not durable. It's durable, it's timber, it's going to last a very long time, but it's soft. And you might not be getting quite the quality you would want to give to your clients. So this is one of the sliding doors, and that is a little vermin pet door for your ants and bugs to come through. So a few final risks. Size does matter. So when you're designing, you need to ensure that the cavity you're insulating allows for the depth of the insulation plus the air barrier. If you put 90mm insulation in a 70mm wall, you're wasting all of that insulation. It's not going to work. 70mm versus 90mm frames. I no longer do external walls in 70mm because you cannot get enough insulation in them. Condensation is a major issue. I use mechanical solutions. I don't do passive house, so I can keep that under control. I don't need to use a full air system, but I do need some mechanical assistance to make sure that the house doesn't become a mold trap. Same with internal or indoor air quality. You need to address that at design stage, not afterwards. Maintenance of external frames. Where if you're using timber frames on a 3rd-story building, 3rd-story level, with no access for maintenance, you're creating a safety risk for the occupants of that building later on. Same with cleaning of the glass and cleaning of screens. Make sure you address these issues in design stage. What about everything else that I haven't discussed? Building fabric, colour schemes and building fabric. So this has a big impact on your design, but you can work around constraints. The little project that we've just seen, I had to do it in brick veneer with brick on the outside, which I don't particularly like, but that was a constraint of the development and I couldn't do anything about that. We still achieved 9 stars, so it is possible. Eave depths and window awnings, very important for your solar orientation. Natural ventilation. Natural ventilation doesn't come into your assessment because people may not open the windows when they're living in the building, but it's a very important part of the design. Ceiling fans, we should use them in our climate. Every room should have a ceiling fan. Appliances and soft furnishings, they're removable. They don't come into the assessment, and nearby shading is also removable, so isn't used in the assessment. Doesn't mean you shouldn't use those things. They're very useful tools, but they're also after the fact. You should address the issues very early on. That's all from me. Thank you very much.
Thanks very much, Esther. Fantastic presentation. We've got a lot of feedback, great comments. We've got a comment from Jeremy in Tasmania. Exciting project. Do you follow your projects to see if they perform as planned?
I'm hoping to, yes, very much so.
Well, that's great. And I think, you know, when we look at Australia and we look at the climatic zones, I think a lot of people, you know, I guess consumers think that it doesn't matter where you are in Australia, if you build a home, whether you put it in New South Wales or up in Cairns or in Tassie, you can just build the same home in all the areas. And I think it's really, really important that the designers, I guess, emphasise the importance of the different climatic zones. And I know through NatHERS, there's currently 69 different climatic zones. And I mean, in Australia, I guess there's really just 8 in general, but using the NatHERS system, there's 69. So I think if people were using the 8 as opposed to the 69, you have massive changes between projects.
Yeah.
The other important point, Esther, is it's not just the products that you put in, it's how they're installed, because it's great to have a great insulation, but if it's not installed properly, it can be useless, as you said. So it's got to be something that people really do look into as well. You might specify it, but is it actually being installed properly?
Yeah.
To get the, I guess the maximum value out of, or R rating and so forth out of your product. So Esther, thank you once again. And you're not in lockdown up where you are you?
No, we're free for now.
Oh, good.
My sympathy.
All good. Thanks a lot, Esther.